Okay, class, let's continue to the constraint optimization today. As you know, the problem of the constraint optimization is like this. Minimization of your function such that there is inequality constraint, equality constraint. That's the typical form of the constraint optimization, where x is sorry, this is more correct, where x is an open set such as a real number and gx is a vector actually, this is more right, n so for example, x is n-dimensional real number, and each function g sub ix will map this n-dimensional real number, n-dimensional x, into a one-dimensional one. But we have m g functions here, so it's a mapping from n dimension to m dimension. Same thing here. The equality constraint is also given like L. It's a mapping from n dimension to L dimension. Okay. Now we have this kind of constraint. Unlike the unconstrained optimization problem, our feasible reason is not the x. Now the feasible set S is defined as, the mathematician like to use this sign, which means definition such that that's our feasible set. Okay, and recall that we define the x bar, a specific point in a feasible set, is a local minimum of problem P if there exists very small epsilon such that within a very small adjacency area, which is a 4 or y, the B means bore centered at x bar with the radius of very small epsilon, and S cap B. S is our feasible set. So in the intersection of this feasible set and the very small bore, if there exists a small epsilon, and for that every y inside of this S intersection B is less than, greater than the function value at x bar, then this x bar is defined as the local minimum of constrained optimization problem, P. It's just a simple, very straightforward extension of unconstrained optimizations problem definition. Okay. All the definition we covered for the constrained optimization can be analogously extended like this. If you put intersection of feasible set and the bore, then you can extend the definition for global minimum, local maxima, global maximum, and the like. These are just the same. You have to think about is now we have constraint. Because of that constraint, our feasible set is reduced. Okay? That's it. Okay, that's the only differences in the constraint optimization problem. Okay, one simple example. Let's say we are now talking about two-dimension, and let's say there is some contour, surface function like this, and let's say this is the minimum value. In unconstrained optimization, once we are given an initial point, we know if we follow the descent direction with appropriate step size, we will eventually approach this local or sometimes global minimum. The concept is exactly the same, but for this constrained optimization problem, we have to consider that we are only feasible in this S. For example, this inequality constraint, let's say there is some function like and for example, this will look like this. The y section is 100 and it will look like that. And let's say if this is our constraint, then we only have to consider this region. Right? Or let's say there is another constraint such as that's another inequality constraint, right? And for this, we have to consider only this region. Okay? The problem occurs because of this constraint. For example, our feasible region will be in this region, right? Okay. 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 And do you notice anything special about this? If the function is nicely defined, I mean continuous and multiple times differentiable, and it's a convex, then you can easily find the optimum. For example, let's say this is your initial point, and you can just utilize your steepest descent algorithm to find this minimum. No problem at all. Really? Have to think very carefully because you are confined only inside of this feasible vision. Okay. This is an easy example, and so I'd like to change something. Let's change our objective function, and let's assume our real minimum is around here, and the function will look like this. Okay. Now the problem gets a little bit more complex. Assume that you're given here as an initial point, and if you follow the steepest descent direction, well, you may go here at the first step, and at this point your steepest descent direction is around here, and maybe ends up your line search will point some out of feasible set location. Have to consider this. Okay? Also, but this part is easy part, because if we manipulate a line search algorithm a little bit more, then you can just put a fixed boundary. So you can easily make your algorithm stop at the boundary. Okay? Well, that is then at this point you are also supposed to calculate the steepest descent, which is also gradient of the function. And for now, let's assume the function is continuous like this, and there is gradient. But sometimes your objective function will not have any gradient at the boundary. Okay? But anyway, looks like this is your gradient direction. Steepest descent direction. But you cannot move that direction because it's not feasible. Then you need to consider that even though it's not the steepest descent direction, you have to first search the descent direction. Okay? This range are all the descent direction, right? And you have to think about the steepest possible descent direction within this feasible set, which will be this direction, right? And I think that point is the local minimum of this constraint optimization problem. So for this example, I indicated that we have boundaries and we sometimes cannot move to our desired direction because it's not feasible. So direction is also a problem. We need some special consideration in determination of this direction. Also, I mentioned that have to be very careful about this line search, right? And a little complex one is that have to be very, very careful about the definition of convex and convex function. Even though this is your very well-defined convex function centered at 0, like something like that, okay? Circular, and at the origin it will have the global minimum, and this function is convex function in unconstrained feasible region. But however, sometimes it is possible your feasible region is look like that. You are only allowed to move in this shape of the feasible set. Then you will have to consider a little bit more. You have to pay a little more attention. Is this convex function or is this convex set? Even though our x is convex, our function f is convex. Because of this constrained feasible region S, we have to think about this convexity of the set and convexity of the function. Okay, that's what I'm going to do during this class. And because of this direction limitation, I'd like to define one more concept, which is a cone. A set C, which is a subset of this X, is a cone if for every x inside of C, alpha x inside of C, for any alpha greater than 0. Geometrically thinking, let's say if you have a very simple plane, so R square location, and let's say your C is defined like that within this, between this, and in this direction you're not bounded. Whenever you pick an x, alpha x also inside of this, right? That's the cone, because the shape look like this cone, and so mathematically it's defined as a cone. Okay? Set C is convex cone if C is a cone and C is convex set. Simple. The example I showed before this is this just a cone or a convex cone? The region between this. Okay, everybody so sure this is a cone, right? Is this convex set? Oh yeah, whenever you pick any 2 points within this set, the line connecting these 2 points are all inside of this set. It's convex, so it's a convex cone. Okay? Okay, based on these two concepts, I'd like to define a little bit more thing. F sub 0 F sub 0 is a set of a direction vector which satisfy this form. And this form is descent direction, right? If this is less than 0, then your D is in the opposite direction of, gradient. So it's a descent direction. So mathematically defined here, and we call this as the cone of descent direction of F at x bar. And this is defined as we have a GIX, right? And I is a set of these small i's, the set of indices. The indices of binding constraint. And large G sub 0 is a direction. For all I inside of this I, large I, which means this I is now the all indices of binding constraint. So this means for all binding equality constraint, you have some kind of descent direction. Okay? But it is not true, mathematically true, to call this as a descent direction, but now we call this as the cone of inward direction of binding constraints. large H sub 0 is also a set of direction which satisfy gradient H sub I transpose D keep that in mind. This G we mentioned inequality constraint. For the H we mentioned equality constraint. Okay? So this is inequality constraint. So as I mentioned before, like the example, because of the inequality constraint, there is some region like that. For this G1, we only have to consider this direction part. How do you define this direction? Like this. Large G sub 0. For this G2, we only have to consider this direction, right? For this linear inequality constraint, the direction is only one, right? I mean, the perpendicular direction is there are only one. But for this quadratic function, quadratic inequality constraint, the direction will vary according to the location. So it is defined as your x bar. For example, your x bar is here, the current position is here, and the range of this direction is G sub 0. Okay? Okay. Let me first introduce what is the binding constraint. Okay? If you are here, you do not feel any boundaries. You can freely move here and there a little bit. Okay? But if you are here at the line, you cannot freely move in this direction because you're bounded by this G1. But you are not bounded as this G2. So for this specific point here, your binding constraint is G1. If you are here, your binding constraint is G2. You don't have to consider G1 at this point. Okay? But if you are in the intersection of this G1 and G2 function here, your binding constraints are G1 and at the same time G2. You have to consider this both constraint function. So if your x bar is here, your large I is 1 and 2. The I means the indices of binding constraint, right? Your binding constraint is a G1 and G2, so large I is 1 and 2. Okay? If you're here, your I is also 1 and 2. If you're here, your I is only 1. If you're here, your I is just 2, right? It depends on your current location. Okay? So this one is clear. And about this G sub 0 is for your binding constraint. Okay? Let's assume you're right here. Your binding constraint is G1. So you only have to consider the G1 part here. Okay? So I defined it like this. 100 minus x is your g1, and gradient is minus 1. It does not depend on your location, right? Am I right? Okay. And what would be the d which satisfy if this is your x1? Okay. I need volunteer, but I said like this: y is less than or equal to 100 minus x, and we have to follow this form here, and should be less than 0. So it's a y minus 100 plus x, right? And this is your g. Right? Because if you write this form, this small x means actually x comma y, right? Okay. Can you calculate the gradient? What is a gradient in 2D space? Anyone? Yeah. Gradient operator is del xi del y j, right? If you put this gradient operator to that gxy, then what do you have? What? 1 and 1. Really? 1 and minus 1? Oh, yeah, 1 and 1. That's your gradient direction. Okay? So, we said this is your x bar. And 1 and 1 vector is here. Right? And if you make this gradient dot d is less than 0, then if this is, so it's basically perpendicular, and if your g is in the range of here, then this will be satisfied. So it's an inward direction. Same thing here. Because this is a linear function, you don't have to actually put any x and y in this gradient value, but however, you will get those kind of function if you apply the gradient in this quadratic function. However, put the exact x and y, x bar information there, and you will get the same information. So g is your cone of inward direction. Direction, not cone. Cone of direction. So this is your cone, right? Cone of direction. Okay? So that's your region. And for this, H is for equality constraint. Okay. We have G1 and G2, and within this region, this is our feasible region, but at the same time, we have equality constraint. Let's assume there is a equality constraint like that. And G1, it's a y minus 100 plus x. And for G2, y minus x squared. Okay? And for this H1, it's a y minus x. Which means your feasible region is inside of this part from the inequality constraint. But from the equality constraint, now your feasible region is reduced on this part. That blue line. Because this is your equality constraint. Your point should satisfy that within the region at the same time on that function. Okay? Okay, having said that, what would be this H? For now, we have y minus x as a h1 x comma y. Gradient of this h1 at some point is 1 minus 1. Oh, sorry. Minus 1 comma 1. Right? And in order to have these two vectors have the 0 in a product, then okay, there is a vector like this. Is this vector A? And you have to draw vector B, which satisfy what would be the vector B? What? Orthonormal? Okay. Right? Really? What? Come on. Opposite direction? I mean for general dot product. Okay. What is it? And what's the next? This is theta, right? Okay. Then how do you satisfy this? This is not 0. This is not 0. You have to make this 0. And what's the theta?
0 or
This is cosine. This is 0. This is 180. Now, as Simon said, have to be perpendicular to each other. Come on. Okay? This is gonna be B to satisfy that. Okay, you have this direction. Okay? And if you draw it, then what's the vector here? It should point -1 and 1. Okay? And there is a 2 direction. And recall this is the set of tangent direction. Of equality constraint. Right? We are only allowed to move in this direction inside of G sub 0, and for this equality constraint we are only allowed to move in this H0 direction. Right? Okay. And I mentioned before, we have to consider variety of things because this is the constraint optimization. First thing is we have to consider the direction. We cannot just follow the descent direction because sometimes, because of this feasible set, our direction is limited. And the next thing we have to consider is the line search. And the other thing is convexity. Okay. First thing, with this information, we have enough tool to actually calculate the direction inside of our constraint optimization. Okay. So there is one theorem. Is assume that hx is a linear function in another word, hx is ax minus b for it's a generalized linear function. Since x is in n-dimensional space and h is, we said, n to l, right? And x is in n. So a should be in this dimension, right? If x bar is a local minimum of problem P, then this should hold. F0 intersection G0 intersection H0 is empty set. Proof. At x bar, the gradient of the h sub I is AI. Based on that fact, h sub 0 is right? Okay, suppose D belongs to this F0 intersection G0 intersection H0, then for all lambda which is greater than 0, sufficiently small right? For sufficiently small or lambda, if we move from x bar to in that direction D, your GI and x bar should be less than 0. For all binding constraints. And this will also hold. Therefore, x bar plus lambda d is also S for lambda, non-negative lambda sufficiently small. On the other hand, for all sufficiently small lambda, non-zero lambda, f x bar plus lambda d should be is less than fx bar. and this contradicts that this is local minimum of P, so it is empty set. Mathematically, this is proof. However, let's go back to the simple example once again. Let's say there is a function like this. Okay? And let's say this is your inequality constraint. Okay? And let's say this is your equality constraint. Okay, you are only allowed in this region by the inequality constraint, and you are only allowed to move on this line by your equality constraint, and this is your minimum of the function fx. Then, well, without the equality constraint, we can just pick that this is the minimum. Inside of this blue region, this is the minimum, right? But if we also consider the equality constraint, the line should be on this red line. I mean, the point should be on this red line, and I think this is the minimum in this our feasible set. Okay? Okay. At this point, let's say this is x bar. I will draw this point a little bit larger here. This is x bar, okay? And f0 is the descent direction, cone of descent direction. So at this point, well, maybe this is the cone of descent direction of this function. So let's say this is your cone of descent direction, right? This is only from this f function, f, right? Based on this contour line, okay? And the indices of binding constraint of inequality constraint. So for now, we only have to consider this first inequality constraint here. And for that, the cone of inward direction of function g1. And this cone of inward direction is this, right? So this is your cone of inward direction, right? And H0, it's a set of tangent direction of equality constraint. What's the tangent direction here? And Okay? Red. Those are tangent direction. Right? If you only choose the one tangent direction, well, actually, this is the tangent direction. Minus 90 degree also. Okay, anyway, there is something incorrect, but anyway, the mean is that if we neglect that part, there should be no intersection at all. I mean the empty set. So the intersection of this blue cone and black cone and this red line should be empty set. Okay? So based on this equality constraint, I'm not sure which part was gone wrong, but if you follow this direction on this equality constraint, it will be the descent direction. If you still own the equality constraint, so that's the meaning of this h sub 0. But anyway, the important thing is it's empty set. There is no other way to move. If you still have the direction to move, then you can move to that direction. Okay? So a famous two kind of necessary condition. One is Ritz-John necessary condition. And let X bar be a feasible solution of problem P. If X bar is a local minimum, then there exists this U sub 0 U V such that U sub 0 times gradient F X bar plus U transpose gradient G X bar plus V transpose H X bar is equal to 0. And U0 and U are greater than 0, and U0, U3 is not 0. And UI, GI, X bar is 0 for i는 I equal 1 to M. Okay. Okay, proof. If vectors gradient hi x are linearly dependent, then there exists non-zero V such that V transpose, right? And setting U0 U is 0, then you will get that one. Also, suppose the vector gradient h sub i's are linearly independent, then for this we can utilize this. Sorry, that's our empty set. Okay. These two approaches are how we can prove this theorem here. Detailed steps will be in your lecture note, so please refer to the note. And this is actually, the concept is really simple. We just show that this is true, then it is local minimum. And it's nothing more than rewriting of this condition in more generic form. Okay? Okay. And this is one necessary condition, and this is more famous condition. We call KKT necessary condition. KKT stands for some name, in short. Anyway, let x bar be a feasible solution of P, and let I is indices of same thing. Further, suppose that gradient g sub I for n, gradient h sub I for the binding constraint are linearly independent. then if x bar is a local minimum, there exists uv such that which is u is non-negative and ui gi is 0 for I. Okay, this is most important necessary optimality condition in constrained optimization. Okay, let's go back to the concept talk. What do you think this stands for? Ui times Gi. Okay, and then gradient fx, gradient gx, gradient, and as we talked before, our feasible line is here. This is, so if you focus on this point, okay, that's the F0 direction, and this is your G sub 0 direction, and these two are your H sub 0 direction. So that's the conceptually most important thing. If it's not non-zero, which means there exists some direction. If you follow that direction, your function value will be decreased. So since we are talking about the constrained optimization, as I mentioned before, the gradient of the f cannot be our optimality condition anymore. If those local minimum or local minimum is within our feasible region, then we can apply it, but it is not generic enough to tell this is really an optimal point or not. This is the most important concept here. Even though the function value and even though the gradient of the function value is not zero, it's non-zero, but you cannot find any descent direction, then it's your local minimum. That's the point here. Okay? And this one includes the descent direction information. And this one includes the inward direction of your constraint. And this one includes your tangential direction of your equality constraint, which means fx means, well, if you go this direction, f sub 0 direction, the function value will be decreased. It has the information. If gx, you can only move in this direction because you're bounded. And this one means you can move only that direction because you're bounded by equality constraint. If this has intersection is not, if there is a direction which satisfies all this, then that's the direction that function is decreased. So you can go to that direction. If that direction exists, then our point is not the local minimum. That's the point. So mathematically, the form is really simple. But what they are saying is exactly the same as this. Okay. That should be 0. The format is really similar to each other, but however, in order to prove this KKT condition, you have to utilize this one first. And this is really useful optimization necessary condition. And I will skip the detailed proof because we don't have enough time and everything is on your lecture notes. And yeah. Okay, for the housekeeping, did you receive the homework number 6? Okay. Any problem? It's about the unconstrained optimization only. If you truly understand how you can write a program to solve a unconstrained optimization, you can easily expand your skill to the constrained optimization. And I intentionally put the Newton's method and steepest descent method. The algorithm should be a little bit different to each other. However, you can utilize same line search function. Line search method, well, do not have to be different in each of the algorithm. For example, if you use Amiho rule, then you can use that Amiho rule for the steepest descent or Newton. Okay, so I strongly recommend you to write a structured code. Okay, save your Amiho rule as a different M file. Save your exact line search as a different M file. And save your function evaluation or gradient evaluation, Hessian evaluation in each different M file. And make your steepest descent algorithm as different M file and Newton method as a different M file. And your problem M file, you can just call these relevant functions inside of your problem number 1 M file and solve it and proceed it. By doing that, well, first of all, it's really easy for us to grade. If you put everything into one single M file, then TA will struggle to grade it. Okay? So, okay. Thank you.